So far, Chapter 5 has been about techniques of integration which counterbalance all of the derivative techniques. For example, a derivative technique we learned was chain rule, right? So if you're going to do the antiderivative of that, you need the anti-chain rule. Now, it's not its official name, but we learned the chain rule, and we got to be able to run it backwards. So what if we've got a function that's nested in parentheses? We know how to do derivatives using the chain rule, but how do you do it, the antiderivatives? So that was the first day, and we learned the technique of using U substitution. And that is when you've got different embedded parentheses that would normally require the chain rule for derivatives, and so when you're going the other way, you use a U substitution. We've learned the product rule for derivatives. When we notice we have a product, and so now U substitution doesn't work on a product very often, and so then we need the anti-product rule. And so there you've got the options of using parts or tabular integration, depending on if your part is a polynomial, then you can skip right to tabular. But if either of the parts was log, or if you didn't have a polynomial part, then you can't do tabular. So then that leads us to partial fraction integration, and that's the quotient. So if you have a quotient of something, well, you're going to need an anti-version of that in order to be able to do an integral. And so in that case, we are going to use partial fractions. In the technique of partial fractions, 90% of it is algebra, and only 10% of it is actual calculus. So it's more an emphasis on an algebra technique, and a very, very small part of that is actually any calculus at all. So I assigned you some partial fraction problems just to kind of dust off. You haven't done it since HAM, so it's been maybe a year, if not more, that you have done since you've done partial fractions. That's why I assigned it. Or maybe just a couple months. So you should be a pro. Okay, so that technique comes in handy when we need to integrate a quotient. So here's a quotient. 2x plus 16 over x squared plus x minus 6 dx. Now you still want to consider U substitution for this, if possible. So I would at least take a look at U substitution. U substitution for a quotient, your U is almost always going to be your denominator. So if we chose a U substitution here, hopefully it wouldn't take you too long to figure out that 2x plus 1 is not good because of the 2x plus 16. Now, if it had worked out perfectly and it was 2x plus 16, well then for sure U substitution is the way to go. But in a situation like this where the du, the differential, is not helpful in reducing, then we realize that the U substitution is not the right option. And so it's going to be partial fractions. So here comes your 90% algebra. Where you take the 2x plus 16 over x squared plus x minus 6, and you split it into partial fractions over the two different factors of the denominator. The denominator can be factored into x plus 3 and x minus 2. So then you're going to perform partial fractions. You'll get the common denominator, you'll solve for A, you'll solve for B. All right, so then the algebra, this is where the 90% algebra comes in, where you get the common denominator. And so we're going to multiply A by x minus 2, and we'll multiply B by x plus 3. That's going to give me ax minus 2a over the denominator, x squared plus x minus 6 plus bx plus 3b over the denominator x squared plus x minus 6. So now I've created a common denominator between the two, still equal to the original function, 2x plus 16 over x squared plus x minus 6. When I combine and I consolidate, I'll have the common denominator x squared plus x minus 6 equals, and what I will end up with, if I put it in the right order, is ax plus bx minus 2a plus 3b. So I group the x's together. When you put something in the right order, all the x's have to come first. And then on the other side, I still have the numerator of 2x plus 16 and x squared plus x minus 6. Then I look, because the denominators are the same on both sides, the numerators must be the same on both sides. They are equal. So therefore, 2x plus 16 as a numerator must be equal to ax plus bx minus 2a plus 3b. We know the denominators are equal. Since the denominators are equal, therefore the numerators must be equal. Since the numerators are equal, the terms must be equal. So the x terms on each side must be equal to each other. And the constant terms must be equal to each other also. Okay? Equality on each side means the terms on each side must be equal. Therefore, the constant 2 must be equal to a plus b, because they all share an x. And the constant 16 must be equal to negative 2a plus 3b. And then you're going to solve. This is what I'm talking about. 90% of this is going to be algebra. You can solve this using any algebra technique you want. Some people like substitution. I usually like elimination as my option. So if I was going to do this as an elimination problem, I would double the top equation. And the top equation would give me 4 equals 2a plus 2b. And the bottom equation would give me stay the same. And the reason I would double it would be for what purpose? If I double it, what would happen? The a's, will cancel out. And so if I double the top equation, the a's will cancel out. I'll be left with 20 equals 5b. Therefore, b must be equal to 4. And if b is equal to 4, I can go back to the original equation and see that a had to have been equal to negative 2. This is what I'm talking about. 90% of this is algebra. So where does the calculus come into play? The calculus comes into play, in that the original equation, which was 2x plus 16 over x squared plus x minus 6 dx, is equivalent to the partial fractions I just discovered. And I determined that negative 2 was over the denominator x plus 3, and 4 is over the denominator x minus 2, and that these two things are equivalent. 90% of the algebra tells me that this original quotient can be split up into two partial fractions. Each of these partial fractions now has an antiderivative of its own, which is where the calculus comes in. And so negative 2 over x plus 3 has an antiderivative of negative 2 times the natural log of x plus 3. And the second one has an antiderivative of 4 times the natural log of the absolute value of x minus 2 plus c, and my answer's done. So that was the 10%, maybe even 5% of it is calculus, and 95% of it is algebra. It's not very. So that is the antiderivative of the original quotient. Yes? No, that's why I was asking you if you wanted me to show them all. So I showed them all for you. And if you can do it in your head or whatever, okay? Yeah?
So the very first
Yeah, so because most of this is algebra, I want to show you different things that show up in the algebra. You don't need to know very much about the calculus, but let me show you some of the algebra stuff. All right, so another one would be like this. Okay, if you were working on the integral of 6x plus 7 over x plus 2 squared. So here's a situation where the denominator is not two distinct factors, but two factors that are the same. So then what do? So the 90% of the algebra comes in here, or even 95. Okay. What you do when you've got a 6x plus 7 over an x plus 2 quantity squared, okay, that's going to separate into the first denominator would be a single x plus 2. The second denominator, okay, if it was also just an x plus 2, if that was true, what would the common denominator be? X plus 2, but the denominator is not x plus 2. The denominator is x plus 2 squared. So at least one of them has to be the full x plus 2 squared, otherwise you haven't forced the common denominator. So this is, I just wanted to show you this as an algebra sample. So then, which is the only one that actually needs any multiplication? A, right. And I just need to multiply that by x plus 2. I don't even have to do anything to the other one. So I'm going to have 6x plus 7 being equal to ax plus 2a plus b. And then it's really clear and obvious, should be at least, because there's only one x term. And then there's the constant term, there are two of them. So therefore, we know that 6 must be equal to a. And 7 must be equal to 2a plus b. And if 6 is equal to a, then we can solve and we'll get 12 plus b. So b must be negative 5. All right, here comes your calculus part. So 6x plus 7 over x plus 2 quantity squared dx is equal to 6 over x plus 2 plus negative 5 over x plus 2 squared. And it's the integral of that. So here comes the calculus. What's the antiderivative of 6 over x plus 2? 6 natural log x plus 2. What's the antiderivative of negative 5 over x plus 2 quantity squared? Okay, so it's not a natural log, is it? Okay, that is not a natural log. You might want to think of that as negative 5 parentheses x plus 2 to what power? Okay, and so then we raise that to a positive negative 1 and divide by the new power. So it actually is plus 5 over x plus 2 on its own, and then plus c. So don't assume everything's a natural log. It's only a natural log if it's over a linear coefficient. Okay, the last one I want to show you, another algebra thing. Okay, solve dy dx equals 2x y squared plus 1 with initial condition of 0, 1. By the way, what's the purpose of me giving you an initial condition? What will that help you to do? Figure out C. Okay. Now, looking at this, this is called a differential equation. And differential equations are equations that have x's and y's mixed together. How do you solve a differential equation? What's our little mantra? Separate and integrate. Okay, so we want to separate and we want to keep all the y parts on one side and all the x parts on the other. So we do our separate and integrate first. So 2x dx is all that's left on one side. But on the other side, I'm going to be over y and y squared plus 1. I divided by y. I divided by y squared plus 1. That's the separate part. Now there's the integrate part. The x side integrates easy, right? The x side is going to integrate into x squared plus c, so piece of cake. The y side needs partial fractions. So I'm going to have to do some algebra before I can do my antiderivative. So my algebra would be a over the factor y plus, okay, and I'm going to leave you some space because I got to remind you of something. Okay, when the factor has a y that's not just a single, not just a first power, okay, the denominator is y squared plus c. That's different than y plus 1 quantity squared. That's a different ballgame. This is y squared plus 1. It's its own factor. The numerator is not just b, because b is a constant. The numerator is by, and then plus the constant c. Ooh, I better not use c. There we go. Okay. So if it had been y cubed, heaven forbid, then what would the numerator have been? by squared plus cy plus d. Right, don't worry, the algebra's, okay? The numerator has to be 1 degree less than the denominator. So that's the easiest way for me to say it to you. Okay, so if the denominator is single power of y, then the numerator is just a constant. If the denominator is a squared power of y, then the numerator has to be linear. If the denominator was cubed, then the numerator would have to be a quadratic. In partial fractions, the difference between the numerator and the denominator can only be 1 degree. Yeah.
So why don't we do it the last question?
Because it was the factor, it's this one?
Yeah.
The factor itself was still x plus 2. It's still a linear factor. It's a set, you're only looking at what's in the parentheses.
Oh.
Okay, not what's outside of it, only what's in the parentheses. Okay? So this one, what's in the parentheses is y squared.
So why do you have plus cy?
Okay, still doing algebra. We haven't done any calculus yet. All right. What will A need to be a common denominator? Correct. What will the other one need to have a common denominator? It will need y. Okay, still doing my algebra. So I now have a y squared plus a plus b y squared plus cy. All of that over the common denominator y squared plus 1. Okay, now I have the common denominators, right? I should have written that this got y squared plus 1 and this one is getting y. What did that come from? It came from the original problem, which was 1 over y times y squared plus 1. Is that obvious? Can you see now how much one of the variable values is. If all I have is 1, what does that match up to? It matches up to A. Okay, this is a constant, and that's the only constant. Therefore, A must be 1.
What about the B constant?
Okay, yeah, we'll do that. Okay, so we know that 1 must be A. Okay, how many Y's are there on the original side? 0. So 0 must be equal to, how many Y's are on the other side? C. So 0 must be equal to C. How many Y squareds are on the original side? 0. How many Y squareds are on my partial fraction side? A plus B. Therefore, what must B be equal to? Correct.
What are you looking at to get like the A plus B? Like what equation are you referring back to?
Okay, here. Let's focus on this, okay? How about I do this? How about I erase all of this? Okay. I'm going to put this in in order, okay, for you, Justine? AY squared, what comes next?
What?
What would come next if I'm putting that numerator in order?
What's that?
No, by squared has to come next, okay? We're doing order. Powers come first.
Oh, okay.
Okay, what comes next?
Plus C1.
Okay, good. Plus cy. And then A comes last. Okay, that's in order. All right, the other side, the one I have circled in, okay, how many y squareds are there on that side?
0.
Okay, so I'll put 0y squared. Okay, how many y's are there?
1.
I don't see any. I don't see any y's either. 0. And how many constants are there?
1.
It's constant 1. Okay? All right, so now everything's in order, so you're going to match up. This term matches up to these two terms. Okay? Let me find a good. Okay. This term matches up to this term, which means that this term matches up to that term. It's just a matching. It's a one-to-one pairing. Okay? So 0 in the y squared box must match up to the constants a plus b. If I have no y squareds, then that means a and b have to cancel each other out. That's the only way to get no y squareds. In the blue box, no y matches up to c, so c has to be 0. And in the pink box, 1 is the only constant matching up to be a. Therefore, if 0 is c and 1 is a, and a plus b cancel each other out to make 0, okay, then what does b have to be?
-1.
Okay, so now we have a value for a, b, and c. Okay, this is all still my algebra. I better rewrite it. So I had a over y. I had by plus c over y squared plus 1. I had all of that. I just figured out that a is 1, that b is -1, and then c is 0. So I now have 1 over y plus -y plus 0 over y squared plus 1 dy. All of that was just plain algebra. Now I'm ready for calculus. Okay, so here's my, 10% calculus. What's the natural log, what's the antiderivative of 1 over y? Natural log of the absolute value of y. Okay, what is the antiderivative of -y over y squared plus 1? Not quite. Okay. It's not okay. So yeah, you're thinking about all the right things. Is it tangent inverse? Okay. All right. Well, then how are you going to do just this? How did we learn how to do that before? Okay, I need its own u substitution. Okay, just for this little guy. What will u be? Y squared plus 1. What will du be? 2y dy. What's going to happen when I substitute? Okay, it's going to reduce, right? Okay, it is going to reduce. So when I substitute, I will have negative y over u times du over 2y. So what happens to the y's? They reduce away, leaving you with negative 1 over negative 1, I like it better like this, negative 1/2 times 1 over u du. So Cassidy, you were on the right track about needing a natural log. You just weren't quite there. You were close. So what will the antiderivative of that be? Negative 1/2, the natural log of the absolute value of u. So then my antiderivative would be negative 1/2, the natural log of the absolute value of u, which I picked to be y squared plus 1, plus my second constant. And then on the other side, my easy x side of the equation, I have x squared plus my second constant. Oops, my original constant. Then we have an initial condition, which will help us solve. Can we get rid of the two different constants and just write? All right, let's just get rid of it. All right, so my initial condition is 0, 1. So 0 goes in for x and 1 goes in for y, and we should be able to solve for c without too much trouble. Okay, so the natural log of 1 minus 1/2 of the natural log of 2, actually that's 1 plus 1, equals 0 squared plus c. So c must be equal to, what's the natural log of 1? 0. And so c is equal to negative 1/2 of the natural log of 2. That's the constant for c. So my equation is the natural log of the absolute value of y minus 1/2 of the natural log of the absolute value of y squared plus 1 equals x squared minus 1/2 of the natural log of 2. Can you combine those two natural logs, the ones on the y side? You could. What would you have to move first? You'd have to move the half first. What would the half become? Do I need absolute value around y squared plus 1? Why not? Okay, so I can have the natural log of the absolute value of y minus the natural log of the square root of y squared plus 1. And I could even move this one and do the natural log of the square root of 2. I could do that.
Are you going to just do that on this side?
Probably not. And then I could combine these two, and I could say the natural log of y over 1/2 is the same as square root equals x squared minus ln rad 2. Could I get rid of the ln?
Yes.
How could I do that?
Negative ln rad 2. And then
I could raise it to e, right? And I could get rid of the ln. There's a lot of other things I could do. I don't need to. Okay, because we're not going to be able to get y by itself, so we'll stop. Yeah.
Going back to the very beginning.
Oh no. Okay. Yes. Here. Yes.
B, y plus c.
Yes.
Is that just like a rule we gotta memorize? Or like,
Okay.
is there